Hello, and welcome to this presentation on a natural language model for generating PDDL by Nisha Simon and Christian Muise from the Mu Lab at Queen's University. The goal of this project is planning domain definition language generation, which means that given some preliminary text, we predict the next completion using PDDL syntax. A network of recurrent neural networks, or RNNs, was used to build the model. The software for the system was based on Python and PyTorch. The model was trained on a corpus of publicly available PDDL files from api.planning.domains. Therefore, the main contribution of our approach is a language model built using RNNs that is trained on existing PDDL domains and which can be used to generate PDDL-like code. The premise of the project is based on autoregressive language generation, which is to say that the probability of a word or character is assumed to depend on the conditional probability of the previous word or characters. We use an RNN character-level language model to generate PDDL code-like output lines. Various stages of the model are data extraction, data cleaning, data preprocessing, training, optimization, and prediction. Once the training is completed, the predictor can then be run using different starting characters for the output string. Here we see a simplified representation of our multi-layer RNN network diagram. The particular type of PDDL problem domain acted as the category, for example, bartender, ferry, or movie. The bartender problem domain simulates a robot bartender taking and serving drink orders. Ferry simulates a passenger ferry, and movie simulates a movie watching experience complete with snacks. The category and input lines were converted to one-hot vectors. The output was calculated as the probability of the next letter. A dropout layer randomly set part of the input to 0 in order to prevent overfitting. The following is our algorithm used to build an output string. To perform the prediction, we gave the network an initial starting letter and then asked it to predict what the next letter would be. The object of our algorithm is to build the output string based on that given starting letter by using the resulting output at each step as the input for the next step. In this particular example, we see that the given starting character is selected to be a left parenthesis. An output line is generated character by character as shown in the example on the right. The current prediction is used as the next input letter, and this process is repeated until the end of sentence or EOS token was reached, or until a maximum allowed line length was reached. In our experiments, we found that a maximum allowed line length of 70 characters was sufficient for our selected domains. We see that the system takes in the given starting letter of a left parenthesis in this example, and then calculates that the next most probable letter is C. The new output string then becomes left parenthesis followed by the letter C, as shown. The next letters predicted in sequence are H, followed by E, and these are also added in turn to the output string. Since we have not yet reached an EOS token or exceeded the maximum allowed input string length, we continue this process. Having predicted an output string of left parenthesis C, H, E, the system continues adding more characters to the output string based on previous characters. Finally, we see that the algorithm has predicted the letters left parenthesis C, H, E, E, S, E, space, Z, and the number 14, and thus completes the resulting output line by adding a right parenthesis to give a final output line of cheese Z14, which is a valid output line for the movie PDDL domain. Thus, it can be seen that the system successfully produces PDDL-like statements according to the domain on which it was trained. For example, contains short 2, where we see that the system has learned the fact that brackets should be matched, and also that items in the domain can be listed as numeric lists. Another example is short 1, short 2, short 3, etc. The system has also learned that appropriate objects pertaining to the domain, such as chips, pop, cheese, and crackers, for example, for the movie domain, and cocktail, dispenser, and ingredient for the bartender domain, have also been identified. We move on to an evaluation of our system, where we see that the system was trained on a large number of iterations, and as expected, the loss function decreased as the number of iterations increased. The objective was to minimize the loss value, which was calculated as the difference between the correct output and the generated output. Some of the parameters used were a learning rate that was set to 0.0005, a log likelihood loss, and the Adam optimizer. The smaller the loss value, the smaller the difference between the correct output and the generated output, and the greater the accuracy in the material that the system has been able to learn. Future work will include the addition of a greater number of domains and also the use of larger data sets in order to improve the fluency of the generated output. A further extension of the system will be to provide suggestions for the next step as an overall general model is being generated. At a later stage, the goal will be to generate new models of the same class as the training model, but using different objects. For example, the bartender model could be extended to food server. A visualization component, which can be used to demonstrate the probability of the next item being calculated, will also be added to the system in order to provide improved functionality. We pause here to mention Copilot, which is a plugin for auto-completion of code that was released after this paper was written. Copilot is currently limited to the Visual Studio Code IDE. Though systems like Copilot are being developed, we feel that our systems built on RNNs still have their uses. RNNs are more advantageous if IDEs other than Visual Studio Code are being used, when planning-specific constraints need to be placed on the completions, when using a smaller amount of resources, or when there is a need to work offline. We summarize our contributions as follows. We have demonstrated a preliminary step in language generation in the context of generating planning specifications in the planning domain definition language syntax. The goal of this initial work, which was to predict the next completion in PDDL code based on the previous text, was achieved through the novel use of multi-layered RNNs. Generating valid PDDL code is a key component in creating robust planners. Moving towards auto-completion serves to ease the strain of coding on the planning designer, who can then focus on creating the actual content of the plan and not on the creation of the relevant PDDL code. Since generating valid PDDL code is a key step in the life cycle of automated planning research, this ability to generate PDDL code may provide valuable assistance to planning practitioners. It is our hope that the result of this project will be useful for knowledge engineering systems and will serve as the foundation for intelligent auto-completion on the freely available PDDL editors used by the planning community.